everyone. Thanks for attending my talk, and thanks to the organizers for having me here. We'll be talking about environmental effects, and to learn them, we will go through an array tracing exercise. This is me. I'm an Italian living in Amsterdam, and here is my Twitter handle and my GitHub location. So in this talk, we will cover the concept of ZIO environment. There were a few talks that covered ZIO here. We will focus mostly on the environment side of ZIO. We will see how we can use it to build layer computations, how we can test these computations. And with that, we will also learn how a ray tracing application can be built. We will not cover things such as error handling, concurrency fibers, these kind of things. So the agenda is to go through our bare minimum knowledge of ZIO that we need to understand the rest of the talk. We will build some foundations for to solve our problem. And then we will build the components that allow us to build array tracer. We will see how we can test these components, and we will wire things together. And we'll see how we can, bit by bit, improve our rendering and show all the patterns that work. So I will go quickly through the ZIO foundations. You know that ZIO is a functional effect library, so programs are values. So there is a instantiation phase of these values, a combination where you can combine two values. Here you can combine two programs that one will print Zdravo and another one will print Ljubljana. And then we're going to combine them together. And at the end, there is an interpretation phase that goes through that actually will print what we told the program to print. So if you look at the type of our program, we see that it consists of three types. One is the environment, another the error channel, and the output value. So in this case, this program requires console capabilities to print on the terminal. It will not give any error, and it will return a value of type unit. So you can think as a mental model of a ZIO of REA just as a function from R to either of EA. So just looking at the type, we can conclude that about the needs that our program has and what it can do. So we can see that this program needs a console to run, will not produce any error, and will produce an output. But actually, how is it possible that our program that requires a console was able to run? Well, the thing is that the runtime that ZIO provides by default provides already a console. If I use the minimum runtime that I can build, it doesn't provide anything. So the general process is to first satisfy the requirements that the program has by providing whatever it needs. In this case, I'm using this provide method to provide my program that requires a console with a console. And this is reflected on the types. So you see that the program that was requiring a console, now that I provided it with a console, requires any. So I can, it doesn't require any specific type. I can provide it with anything. And this program is able to run on a runtime that doesn't, on a mini runtime, let's say. And the effect is the same. Indeed, if I try to run the unprovided program on a runtime that doesn't provide console capabilities, it will not be able to compile. So the ZIO exploits the type system quite heavily. So how do we introduce in general or eliminate the requirement for an environment? To introduce, there are essentially two methods. One is access, which given a function from R to A gives us introduce a requirement for R and returns us a ZIO of R that can produce errors and A. And if I have an effectful computation, I can use access M. To eliminate the dependency on an environment, I use the provide. So provide eliminates the requirement. useful aliases introduced by ZIO is IO of EA, which is a ZIO that doesn't have any requirements, and a UIO that even eliminates the possibility of failing. So if I handle UIO, I know that this stuff cannot fail at all. Let's see how we can use these little things to build something useful. Given that ZIO has this R parameter, a way of building things that is very handy is using the module pattern. So let's suppose we want to build a metrics service that collects metrics. We saw yesterday how important it is to monitor our applications. So I want to introduce a module that can increment labeled counters, essentially. So I define the algebra of my service through this in this service. I define a trait with a val that by convention we name it with the same name of the module, just a lowercase, and it points to the service defined in the companion object. And then it's very handy to define also an accessor object that is just an extension of the service parameterized on the module itself. So what we are doing here is it's a way to introduce a requirement on our module in any point in the programs that we will end up writing. So with this we are able to write programs in this way. So suppose I defined a log module that is able to log things. I can write a program that requires logs and metrics, and that for every log statement will increase the counter for the statement that I'm printing. So I expect that at the end this program will count once the salutation and once the subject. So the type tells me, you see that it mixes already the requirements, so it needs a log and a matrix. It will need something that provides me both the requirements that I have. And the next step is to provide a live implementation, for example, of this metric service. And what we do, for example, here, this is a Prometheus-backed counter. And I can take the program that I wrote above, just provide it with a mixed implementation of the Prometheus counter and a live logger, and I can just on safe run, and this will run. Another great thing that this approach provides us with is the testing capabilities. So looking at this program, I want to test that this program calls once metrics with salutation and once metrics with subject. How do I do that? So first thing is to define an implementation of the service. Here we back it with a ref. Ref is a construct to handle concurrent mutable state, preserving the functional referential transparency. So I construct the service passing a ref inside that contains a list of string, and for every call to my inc method, I just append the label that I'm doing the call with to this list. And then I can write a simple testing program in this way. I build a ref containing an empty list. I provide my program with a matrix where the service, the val matrix that points to the service, is the one that I created in the case class. So at the end, at this point, I'm able to get back the ref that has been updated by the execution of the program, and I can assert that the calls that I'm expecting have been performed. So when I run this program, if I don't have any exceptions, it means that this test passed, essentially. So these are the minimal foundations that we need and we will use for the rest of the talk. Now let's go to the ray tracing problem. Why am I doing this exercise? Well, in March, VM and John came to Amsterdam and gave us this talk about the death of the Tagless final that was introduced in the environment, the ZIO environment stuff, and was pretty amazing. And I wanted to see how far and how complex you can build application following this approach. And at the same time, I was reading a book about recreational programming, so how to build fun stuff in your spare time. This book talks about building a ray tracer. So I will tell you how it went, essentially. So in a ray tracing problem, we have three things. We have a world built of spheres, planes, shapes in general. Then we have some rays that come out from a light source and hit this object. And when they are reflected, some of these rays can end up hitting a camera. And some other rays, like the one above there, can go somewhere else. And the only ones that we are interested in are the rays that end up in the canvas in front of the camera. So every ray that comes in will color the canvas. And at the end, we want the picture of the world that we see is given by those pixels, essentially. So there are two options here. One is to compute all the possible rays in the world, and then consider only the ones that are in the little fraction of the canvas in front of us. Another one is to have the rays going out of the camera through the canvas, and then if they hit an object, go backwards and say, how was that ray generated in the first place? So we will follow this second approach. So, foundations. A ray is just a set of points with an origin and a direction. So the first thing is to define points and vectors, and way to transform points and vectors. So translate, scale, and rotate. It's natural to define vectors and points through case classes and provide them with the basic operations that we learn in high school. And we can also start using ZIO test features to property-based test the fact that, for example, vectors form a group and vectors and points form what is called an affine space. So the space of applied vectors in given points. And the equation that we saw before that defines the array can be one-to-one translated in code very easily, as we see here. The next thing is transformation. So provided we have a type that models an arbitrary transformation, I define the first service that I need that allows me to apply this transformation to a vector or to a point, and also to compose two different transformations. So we follow the module pattern that we saw before. We define a trait with a val pointing to the service in the companion object. This is a standard approach we will follow through the rest of the application. And then we define the accessor module. Actually, the implementation you can find in the repo for this service in AT module contains like 12 methods. So doing this accessor object for 12 methods is pretty tedious and repetitive and even error prone. Luckily, if we annotate the service, the module with accessible, and we provide as a string the name of the object, the accessor object we want to use, in this case we will stick to the convention to name it with a bigger than symbol, then we can just have just focus on our algebra and our module definition. And this is all I need to define and to write programs in terms of this algebra. So I can, the same way we did before, start rotating, create a rotation transformation, and then apply to a given point, and then get the rotated point, essentially. And again, ZIO will give us all the requirements that we need. Now, how do this transformation? How can these transformations be performed in live? So, if we adopt a convention that a vector maps to a column matrix where the last value is 0 and a point to a column matrix where the last value is 1, then all we need is matrix multiplication, nothing more than that. So we can, provided we have another module that supports matrix multiplication, we can already define a live implementation of our transformation module that is relying on this other module. So here we have a dependency on one module on another. So how do we introduce that? It's just about in the live implementation of the transformation module, and we can rely on the matrix module in the for comprehension. So I just take if I want to apply transformation to a vector, I have just to make it a column out of that, multiply it, and then go back from the column matrix I have back to the vector, and that's it. So let's try now to run this program that we just wrote. So let's try to provide it with our live module that we just wrote, and the compiler tells us he forgot to provide me with a matrix module service. So we just follow what the compiler tells us. We have just to mix it in with the live version of our matrix module, in this case with a live version that is backed by Breeze, which is a Scala library for doing this kind of computations pretty fast. And then this compiles and even runs. And this is enough already to build this kind of rotation, translation, and scaling transformations. Now, we have enough to start thinking about building a camera. So the first thing to consider is that, everything is relative. So it's the same thing to look at a sphere centered in 0 from a camera in -3 than looking at a sphere in 3 from a camera in 0. So we define what is defined as a canonical camera. So it's a camera that always looks at the world from the standard position. And then, in general, we can define it in this way. It looks at the world from the origin of the axis, looking towards the negative z, and always looking up. This vector up is necessary to cope with the rotations of the camera, essentially. And any other camera can be defined in this term, and is the same thing to look at the world from a camera in an arbitrary position than looking to the world from our canonical camera after we applied the opposite transformation to the whole world, like we saw with the translation of plus and -3. So I'm able to make an arbitrary camera by defining the transformation that I have to apply to the world, given that I'm looking at it from the canonical camera. You see, for example, here that we are translating of the opposite point that the camera is looking at the world from. I compose it with a rotation transformation that copes with the fact that the camera can rotate. And then I put this transformation inside the camera object. And I build, with this I build an arbitrary camera. So it's transparent from this make method that all we need is capabilities to perform geometrical transformations. And this canonical reasoning is, we do it for the camera, we do the same also for shapes. So after we define a canonical sphere, which is a sphere centered in 0 and of ray 1, and a plane, which is the horizontal plane, we can define any other sphere and any other plane just by embedding the transformation that takes the canonical one and makes it whatever we want, for sphere and for plane. So let's see how we can make an arbitrary sphere placed in an arbitrary point with a given radius and with a given material. So we have to scale the sphere in all the axes of the same, of the radius, essentially. Then we have to translate it, and we take that transformation and we put it inside the, we compose them, we put them inside the sphere, and we have the sphere. And for the plane, we do the same thing. And this is all we need to build an arbitrary complex world build of planes and spheres. And you see that everything this requires is a transformation module, essentially. Now, let's see how we can build the image that we were looking at. So we need to go through the pixels of our camera and produce essentially one color per pixel. So we define one module that is responsible for this. So this module has a raster method that, given a world and given a camera, will give us the stream of the colored pixels that represent the world as seen from that camera. And we can provide, for example, this is a dummy implementation of our module that would just produce always a white canvas. But how do we produce then a live view of the world? We need two things. We need a camera module that will be responsible for producing an outgoing ray for a given pixel, and another module that is that will calculate the color of that ray once it hits the world. So we will use these two modules, and now we define just the algebra of these two modules. We didn't care yet about their implementation, but this is enough to provide a live implementation of our rastering module. So what do? We just declare the dependency of the rastering on the camera and the world module in the same way that we did before for the transformation. So we just create two vals, one per dependency, and we just use them in our implementation of the raster method. So you see here that we are just calling the ray for pixel provided by the camera and the color for ray provided by the world module. And that's it. Then there is something around to handle the streams. Essentially, for every pixel, we just ask, give me the color for this pixel. Now, we want also to test this implementation. And we can test it in the same way we did with that metrics module. So first, let's define a method that we want to test. In this case, let's suppose we built the world and we have a camera. We want to check that the pixels are the ones that we expect. So we run our stream, and we just call a run collect that will just give us the list of all the pixels that the stream emitted. And then we will be able to assert on this list and check if it gave us the right colors. The next thing we do is use a slightly different approach than we used before, but it ends up is always backed by this ref thing. Just we don't have to do it by hand. What we have to do is just annotate the modules that we are depending on as mockable. Then we define some expectations for this for the methods that we are calling. So we are expecting that when I call the camera module ray for pixel for a given pixel, it will give me the ray R1, and the same when I call it for pixel 01, it will give me R2. And the same thing I can do for the other module that I'm depending on. So when I call the color for ray R1, I expect to have red, and when I call for color for ray R2, I expect to have green. So I just define how my modules I'm depending on should behave. And then I can take the program I want to test and provide it with a rastering module backed by the mocked services. Okay? Instead of provide, we use this provide managed, which is slightly different. So we do this provide managed, and then we zip the managed environment provided by the mocked services, and we build the service we are depending in by passing the dependencies that we got there. This provide managed is relates to the concept of managed resource that we have in ZIO, which is handling something that has an acquire and a release phase. So in the acquire phase, you load the module, you load the mocks, and you define their expectations. In the release phase, you want to assert that the mocks have been called accordingly. And this is all embedded in this usage of provide managed. The last thing we have to do is just assert on the results. So putting things together, you see that this way we are fully testing that that our program is doing what it's supposed to do. And we did this remaining pure and functional without having any reflection or limiting probably the number of surprises we're going to have. So what we did here is to implement one module in terms of underlying modules and test only that interaction and bother only about that. We don't know yet how we're going to color those pixels or how we're going to produce those rays. But we are already able to test that our canvas can be colored the proper way. And from now, it will be just modules all the way down. So we're going to go crazy with adding modules and modules. So we'll provide a live implementation of the camera. I will not go through details, mainly for time reasons. And let's focus on how we can make the world behave more realistically. So the first thing to do is, so remember this world module is supposed, given array is supposed to tell me the color of this ray. So first thing to do is to see if this ray is hitting anything in the world around. Is it hitting a sphere? Is it hitting a plane? Or maybe it's hitting nothing. And the fact that the ray hits or not, or doesn't hit something is delegated to our world topology module that just deals with the fact of shapes being present in some place in the world. So it deals only with this kind of problem, and it would be also responsible for the fact that when an array hits a shape, that point can be shadowed by another point, by another shape, and this, of course, changes the visual effect. So it will give me two things. We'll calculate the intersection between an array and a shape, and will tell me if a point is shadowed. So, given that, we want also to see how, not only where the ray crossed a shape, but also how, with which angle it hits the shape, because of course this changes the way things get the color that point will have. So we have this, the calculation of these components is delegated to another module, which is the heat components module, that will be responsible for calculating essentially these three vectors. So we have the shape that the ray hits, the point where the shape, the sphere, for example, is hit. It will be responsible for calculating the normal vector to the shape, which is the orthogonal vector to the hit point. The I vector, which is essentially the opposite of the ray, so it's a vector that goes from the hit points towards the camera, and also the reflected vector of the ray, which will be important later on. And then we have to use these components to calculate some color, and this calculation is in turn delegated to what we call a Phong reflection module that will use a Phong reflection model, which is a mathematical model that simplifies the way that light behaves when it hits some surface. So the Phong reflection module will consider the heat components, the point light that describes where the light is, and the fact that the point is shadowed, and will produce some color. Actually, it will produce three colors that cater for the ambient light, the diffusion of the light, and the reflection of the light itself. And then these three colors will be combined together and produce the final color of our shape. We can provide a dumb implementation of this reflection module that says that if the point is shadowed, I will just make it black. If the point is not shadowed, I will just make it white, and that's it. So this is already enough to display a first version of our canvas. So we create a camera. We have a world. Then we create a canvas where our pixels will be colored, and what we have to do is just call this draw on canvas with camera method that will just call our rastering module. We'll ask for the stream of the colored pixel. We'll put them in the canvas through this mapm, which is the effectful. We want to execute a side effect for each of the colored pixels. Put them in the canvas. And essentially, that's it. So after this, we will have colored our canvas with all the colors of our image. So if you take this program and we look at the types, you see that all the dependencies converge together in the environment. So we see here all we need. And so the first thing, if I want to run something, is to satisfy all these requirements. So I will provide you with a live implementation for each of the modules that are declared there. And if I follow this, I see that the compiler tells me all the transitive dependencies that this module have that haven't been satisfied yet. So what I have to do is just follow pedantically what the compiler tells me to do, and keep adding all the modules I need. So I need to provide them with the blocking because I have to write to the file system, with the matrix module to be able to multiply and do this kind of transformations. And we go on and on and on. So we will end up with a pretty huge list of dependencies in this case. The nice thing is that we can group all these dependencies, just creating a trait that combines all the traits together, or a type alias. Now, if we compare this with what we would have with a tagless final approach, we could have followed the same thing and build an application in tagless final. Having this grouping of dependency together is basically impossible in a tagless final approach. So once we have grouped the basic dependencies, we can leave the possibility to change the dependencies only of the remaining modules. In this case, we want to just leave the freedom to change the Phong reflection module. And here we just put the black and white implementation we defined before. And we have this kind of shape. So you see that when the shadow is there, the point is black. When there is no shadow, the point is white. And you see that to build these images, I just had to create a number of different points of view, traverse the programs that calculate the image for each of these points of view, and just run them. To make things more realistic, we will make our reflection module a bit smarter. So we'll have to depend on two other modules which are responsible for dealing with reflected and diffusion. And we provide with a slightly different implementation of that copes with diffused light, and we have already this image. And the only thing we had to do is to swap our black and white Phong reflection module with this live module. Now we want to make things even a bit better to cope with the reflection of the light source. So we describe our material with a few extra parameters, which is the specular and shininess, that make the light that hits a given object cause a slightly visual different effect. So you can play with these two parameters, and you see how the corresponding shapes can change. So you see that I have just to make my module depend on these extra modules. And with a little bit complication on the material, so we want to cope with patterns and stuff like that. But essentially, the calculations didn't get much more complicated than what I've shown you. We are already able to display images like this. So we want also to make things a bit more real by coping with the fact that a shape can be built with also with a reflective material. These materials that we are able to display so far are just reflecting the light itself. But in general, materials should be able to reflect also the world around it. Consider if these spheres were made of a mirror-like surface. So for this, we will complicate essentially our world module with a dependency on a module that caters with world reflection. So essentially, this module will be responsible for calculating how the world is seen essentially by this vector here. So when I'm looking at this point, I want to see how this ray sees the world out there. So how do I do this? I have at the end I will have my module that gives me the color of that point by getting the natural color of the shape plus the color given by the reflected world. I just combine them and I have the final color. So this is the world module depending on the world reflection module. But if we look at the world reflection module, well, this guy needs to be able to see how the world looks from the reflected vector. So he needs also a dependency on the world module. So we had just to introduce a circular dependency between two modules. And with this approach, we are able to cope even with circular dependencies between modules. So we can, for example, provide, again, a dummy implementation of the world reflection module that doesn't reflect anything regardless of the material property of the object. And given this, the same three shapes, but we make, for example, the red very reflective and the green-white slightly reflective and green-orange totally unreflective, I can provide my program with a no reflection module version here, and I don't see any reflection of the world on these surfaces. But what I can do is just swap that implementation with live, and you see how the effect changes immediately. So we saw this by just swapping one part of the dependencies that we had and grouping the other ones through traits. There is another approach which is using the provide sum mechanism, where if I want to provide with a module, I can just with an environment, I can just pass a function from the small part of that environment I want to provide towards to the big environment, and I leave only the remaining part of the environment as a pluggable part. So what I have to do is just provide the remaining part, essentially. So this was the exercise, more or less. And we saw that we can build, in this approach, purely functional testable modular application without having to deal with higher kind of types, type classes, and stuff like that. And especially we don't abuse the notion of type classes, because these modules that we saw have nothing type classy, essentially. They're just a bunch of functions that we want to group together and test separately, isolating our concerns. We can group the capabilities, and we can exploit the compiler to help us doing that. we can provide capabilities one at a time in this way. And also, we don't depend on implicit, so we are more flexible on refactoring and things like that. And yeah, I think that this approach is has a pretty low level entry barrier, so it doesn't require a developer to know a lot of stuff about functional and especially about the type system. For the more tedious part, macros help us, like generating this accessor object or helping us with mocking the modules. They are able to handle circular dependencies. So yeah, I suggest that you should just go and try it out and see how it works. You have another tool on your toolbox if you use this, and for me this was a very yeah, nice choice to try and to propose also to work. So yeah, if you are interested in this, you should just join the ZIO Discord channel. It's a very welcoming environment, and I strongly recommend you to join. And that's it. Yeah, I'm available for any questions. Questions?
Let's allow just one question, because we have a closing panel. There was a bit last-minute alteration of the program. So one question, and then 2 minutes break, and then we set up the closing panel. No questions?
Okay. That's fine.
Thank you. So
Great.
2 minutes
Thanks.
break, and then closing panel.